Okay, thank you very much for the introduction and for the invitation. I'm very happy to talk in this seminar. Every now and then I manage to give a virtual talk here. It's always a pleasure. I'm going to talk about recent work with Ivan Penkov. It's quite recent, actually. We're still finishing the paper. It's not yet on archive, but we hope it will be soon. And the result is a Pieri rule for GL infinity. So what I mean by this is, well, the classical Pieri rule, I want to review a little bit what it is, but essentially it's a result about how to decompose certain tensor products and of simple GLN modules. And it's not entirely clear if there is one generalization for the Lie algebra GL infinity. I will try to explain why. So that's why the title is A Pieri rule and not the Pieri rule for GL infinity. So let me start by saying, by recalling the classical Pieri rule. So I will work over the complex numbers just to avoid any special hypothesis each time. And I will talk about, for the moment, I will talk about the representation theory of the Lie algebra GLN. And so the result I want to talk about, as usual, I will fix a Borel subalgebra, which is just the subalgebra of upper triangular matrices, and a Cartan subalgebra, which is the subalgebra of diagonal matrices. And I want to fix those in particular, right? You usually say, well, it doesn't matter which you fix or whatever, but I want to fix those for a reason you will see very soon. In this category of representations, if you have a simple finite dimensional representation, let's call it L, well, it will decompose as a direct sum of its weight spaces. This is very well known. And L has a highest weight, right? It is characterized by its highest weight, which I will denote lambda. This is all ultra classical. And if you give me any other simple representation, I will call it F for a reason I will show you soon. So if F is another finite dimensional representation, then Hermann Weyl's semi-simplicity result, it's for SLN, but you can modify it for GLN very easily, tells you that this is semi-simple. So again, this will decompose as a direct sum of simple finite dimensional representations, each of them given by their highest weight. And the decomposition in general is quite complicated. It's got symbols appear with multiplicities, and computing those multiplicities requires some combinatorial tool called the Littlewood-Richardson rule. I don't want to get too much into that, but I want to get into a very simple special case. So as I was saying, there's a very special case for this problem which is covered by the Pieri rule, which is when F is either a symmetric power of the natural representation or an exterior power. In that case, this decomposition, it's well known how to do it. You take this tensor product. This is semi-simple, and it looks like this. You start with this weight, lambda is the same that appears here, but then you have to add a few something to get the new highest weights of the simples in here. And these weights that you add, they belong to a set that I call the Pieri set. Okay. And what are these weights? Well, when you take the exterior power, this is some weight of this representation, and you want to such that this sum is again dominant, right? So that this is indeed the highest weight of a representation, and that's it. That's the only condition you need. But if your representation is If you're tensoring with the symmetric power, then you need a slightly stronger condition, which is that, well, if you write it in coordinates, this is that if I wanted to say that this is dominant, I would write this is less than or equal to lambda I plus mu I. But for the symmetric powers, the rule says just this. So I'm writing down in coordinates a rule that is usually written in terms of Young diagrams, right? You usually have this rule where you say, okay, to get these Pieri weights, you add d boxes to the Young diagram of lambda, no two in the same row for the exterior powers, no two in the same column for the symmetric powers. But I want to write it like this because I want to move beyond Young diagrams. I want to talk about GL infinity, and I don't want to start talking about infinite Young diagrams. Okay, so this decomposition is multiplicity free, right? So every symbol appears exactly once. This has been remarked several times as a very important result. And in fact, what the Pieri rule does is it describes what happens when you tensor with what are called weight multiplicity free representations. So these two families of representations and their duals are the only simple reps such that their weight components have dimension 1. Right? Every weight component is at most one-dimensional. With that condition, these are the only representations. Of course, their duals also satisfy this. So you can think of the Pieri rule as giving a description for all this type of tensor products, right? You take a simple finite-dimensional highest weight representation and a second representation, which is weight multiplicity free in this sense I just wrote. You compute their tensor product, and voila, the Pieri rule tells you what the result is. So I want to look for an analogous result for the Lie algebra GL infinity. And for that, I have to tell you what GL infinity is and what it is not. It is a Lie algebra, it is infinite dimensional, but crucially, it doesn't have a very interesting category of semisimple representations. So that's the first thing that we will lose. So that's the first thing that becomes that you need to reformulate in the Pieri rule. But okay, let's talk a little bit about GL infinity. So I'm going to take a shortcut, and I'm going to try to go as fast as I can towards the result. So I'm going to sweep a lot of theory under the rug, okay? And I'll mention a couple of very delicate points that I'm just rushing through, but mostly I will ignore technical problems. So to start, I fix an infinite countable set, which I call I, and I define a space of matrices whose rows and columns are indexed by I, right? So you should think of this EIJ as some sort of elementary matrix with a 1 in positions I and j and zeros outside. This is a vector space. It has a product. It's an associative product, which is the bilinear extension of the usual multiplication rule for matrices. So EIJ times EKL is EIL, but only if J and K are the same. This makes this infinite matrix vector space into an associative algebra. It's non-unital, but it's an associative algebra. And GL infinity is just the Lie algebra associated to this associative algebra. Basically, GL infinity is, for me, infinite matrices with finitely many non-zero entries, and the The bracket is given by the usual commutator of matrices, which is well defined because you just think of it as two finite matrices. You take the commutator and then you pad out with zeros. Okay, so in here there is an obvious Cartan, which is the same as before, the subalgebra of diagonal matrices. And this is one of the first points where I'm sweeping a lot of theory under the rug. The theory of Cartan subalgebras of GL infinity is much more complicated than that of GLN. They are not all conjugate, not all of them split the algebra into weight spaces. Massive complications appear. But if you pick this one in particular, this one behaves quite nicely with respect to all the. It behaves as you would expect. You can sort of extend your intuition from GLN to here. So I will not say anything else other than this is the Cartan subalgebra I fix. And all weight decompositions, etc., will be with respect to this. I will, of course, consider its dual, but I'll consider a restricted dual, which is generated by the dual system to this basis. Sorry, no. I want to consider the full dual, and just say that in here there is a dual system for this. And in fact, whenever I have a dual here, I can write it like this. And even if this sum is infinite, it's well defined because, well, it will be applied to some finite linear combinations of the EII. So I can always use this notation to define an element in the dual of the Cartan. For Borel subalgebras, the situation becomes a bit more delicate. Again, it's very hard to say what a Borel subalgebra is abstractly in this context. Classification is done, but it's really, really hard. I will make our lives simpler and just say that if you give me a total order, a linear order on my set I, then there's a Borel subalgebra associated to this linear order, which is just the subalgebra of upper triangular matrices. Right? So upper triangular only makes sense once you have fixed the order on I. And I want to remain agnostic with respect to this order. And this is why I don't choose I to be the natural numbers or the integers or any familiar countable set that comes equipped with an order. Because different order types will give me non-isomorphic Borel subalgebras, non-isomorphic root systems, non-conjugate. Even if they are isomorphic, they might be non-conjugate. Okay, so there's a huge array of space where things go wrong with these Borel subalgebras. So just to simplify the situation, sometimes I will fix a total order, and once that total order is fixed, I will get a Borel subalgebra, and that will be that. Okay, now I want to give you some examples of representations of this Lie algebra. Okay, so the first is what you would call the natural representation, infinite column vectors, right? So this is similar to the natural representation of GLN. It's got a basis indexed by the same set as that's indexed in rows and columns. The action is given as usual. And this is an analog of the natural representation C to D, right? This is an analog to column vectors. And of course, out of this, you can get symmetric powers and you can get exterior powers. Sorry, I mean symmetric powers and exterior powers of this. And in this case, D is not bounded by anything because the dimension of the space is infinite. There is a sort of restricted dual to this algebra, to this representation, sorry, which is again generated by the dual system to the original one. So this is contained in the dual space of the previous V. It's the analog of the dual of the natural representation. The weights are as you would expect. So they're both weight representations, etc. And again, you can take symmetric powers of this and exterior powers of this. And here's a curious observation. These are not always highest weight representations. Depends on the order you take. The maps might or might not be, sorry, the representations may or may not be highest weight. So V is highest weight with respect to a certain Borel associated to a certain order, if and only if this order has a minimum. Let's call the minimum 1. I will tell you why in a minute. And in that case, V is isomorphic to epsilon 1. So this is why you want to call it 1, because then this behaves just like in the finite dimensional case where the natural representation has as a highest weight epsilon 1. And if you think about it, it makes sense, right? Because the highest weight vector should be the vector that has a 1 in the first position and then zeros in the rest. But for that to make sense, there has to be a first position. For the same reason, this is highest weight with respect to a Borel with this order, if and only if this has a maximum, which I will denote -1. This is how programmers denote the last element in an array of numbers, right? If you've used Python or any programming language, the last element of a list is indexed by -1. And so I want to just use some notation to say, okay, there's a last element. This would, if you have this, for example, your matrix, if it's indexed by I, will have a last column and a last row. Maybe not a first one, but definitely a last one. And in this case, of course, this one here is the highest weight representation, and its highest weight is -epsilon-1. Okay. So these are nice examples. Here's another one. I will take GL infinity with the adjoint action. And again, analogous to the finite dimensional case, this is isomorphic to this tensor product here. And this fits into an exact sequence where, well, the restricted dual is contained in the dual. So there's a trace morphism that's just given by evaluation, right? Take a map in the dual and evaluate it at V. This is surjective. It's going to have a kernel. The kernel is going to be SL infinity, but this map will not split. This is not a split exact sequence. If you think about it in the finite dimensional case, the way you split this map is by sending 1 here to some multiple of the identity inside GLN. And there is no identity here. GL infinity contains only matrices with finitely many non-zero coordinates, and the identity is not one of those, the identity matrix. So this sequence does not split. And this is already showing that you cannot have a semi-simple Pieri rule here, because this should definitely be covered by anything that calls itself a Pieri rule for GL infinity, and it's not a semi-simple representation. Right? So this makes it quite hard to generalize this. You need to think a bit more. I want to introduce another type of representation which has no analog in the finite case, which is the following. So I will take a set A of indices, which is infinite, but its complement is also infinite. Okay, so you split your set of indices into two different infinite sets. If you want, you can take, for example, I to be the integers, and you take A to be the positive, and sorry, better take negative integers and the complement to be positive integers. Then you can form a certain vector space, which is usually known as a Fock space, which is sort of like an infinite wedge, an infinite exterior power. So formally, what I'm thinking about here is a space that is that is spanned by infinite wedges. You can think of this just as formal symbols. And this is indexed by a certain set of indices, which is called K. And the only thing you have to ask for this is that the elements in K that are not in A are equinumerous to the complement of K in A. So you're taking A, replacing a few finite elements with something in the complement. This is what it means. So this index set differs from A in only finitely many points. And you can put on this the action of GL infinity that you would usually put on a exterior power. Okay, so EIJ acts on every wedge separately, every vector separately. So this is a well-defined representation, and for different A's, these are non-isomorphic. Okay, two different A's will define the same. This is called a Fock space. Two different A's will define the same Fock space, even only if they differ in a finite number of elements. So this is sort of, there are several analogs of an infinite exterior power. And these modules, they are highest weight. So this is a highest weight module with respect to a certain Borel associated to an order if and only if A is an initial interval of this order. Right? So if you choose some element in the middle, which has infinitely many elements to its left and infinitely many elements to its right, and you say, okay, A is the set of all elements that are less to this guy, less than this guy. Only in that case is this a highest weight module, because in that case, it is isomorphic to the simple highest weight module, which has, well, basically this, right? And for this to be a highest weight, this is the condition that has to be satisfied. A has to be an initial interval. So here's a funny fact. Symmetric and exterior powers of the natural representation are its dual. Exterior powers of the natural representation are its dual. And Fock spaces are a complete list of GL infinity reps with one-dimensional weight components, so weight multiplicity free, and highest weight for some integral weight. And I have to add this, some Borel. Okay, so this is the complete list of simple GL infinity modules, which have a weight decomposition. Each of their weight components is one-dimensional, and they have a highest weight with respect to some Borel. You cannot ask for it to have a highest weight with respect to all Borel, because the only representation that does that is the trivial representation. Okay, so we have to relax this idea of every representation. Well, we now live in a category where representations cannot be highest weight with respect to any Borel, right? That's the first thing that gets lost. So what is this category? What is this family of modules we are talking about? So definition, a GL infinity module, or actually any module over a Lie algebra, is integrable if for any element in the Lie algebra and any vector in the module, the space spanned by M and G acting on M and G acting on G acting on M and so on. So the orbit of M by the action of G is finite dimension. So let me restate the fact. These five families are the only integrable GL infinity representations with one-dimensional weight components and with the highest weight vector with respect to some Borel. If you don't ask for them to have highest weight, you can get even more. Okay, the simple integrable modules for GL infinity have not been classified, are very far from being classified, but those that have a highest weight are classified. Okay, and among them, these are the only ones which are weight multiplicity free. Okay, so now I've introduced all I need to state the our version of the Pieri rule. Okay, so the theorem says the following. Let L and F be simple, integrable GL infinity modules, which are highest weight. Highest weight means that there might be a Borel subalgebra for L and a different Borel subalgebra for F, such that L is highest weight with respect to the first Borel and F is highest weight with respect to the second Borel. And I'm assuming that F is multiplicity free. So if you reproduce these conditions for GL infinity, this is the same for GLN. This is the same setup as for the classical Pieri rule. Integrable means implies finite. Simple integrable implies simple finite dimensional for GLN. Okay, and take M to be the tensor product. Now I want to tell you what this module looks like. Okay, so then there exists first an order, a total order on I with a corresponding Borel subalgebra and a set which as before I call the Pieri set of this highest weight. So L has highest weight lambda. This is contained in the support of F, such that first, every simple subquotient of this tensor product M is isomorphic to a highest weight with respect to this Borel. And the highest weight is given just as in the classical Pieri rule, with mu in the Pieri set. Okay, so this is saying that the simple constituents of the tensor product, they are the same as they would be in the finite dimensional case. You get them as out of a certain bag. The definition of this Pieri set is the same as in the classical case, whether F is a symmetric or exterior power. And I'm just putting the Fock modules in the same bag as the exterior powers. So the definition of the Pieri set is the same as in the classical case. Now, I would like to say something about multiplicity freeness, right? If this were Jordan-Helder modules, if the Jordan-Helder theorem held for these modules, then I would just say, okay, in any Jordan-Helder filtration that you find, every module appears exactly once. But the Jordan-Helder theorem fails for integrable modules over GL infinity. So this complicates the situation. So I have to take a sort of roundabout way to state non-multiplicity and multiplicity freeness. And so it's this. If you give me a filtration, or rather a chain of submodules of M with simple quotients. So I'm saying chain and not filtration because the order type of this filtration might be more complicated than just something inside Z. Okay, it might have several extreme points. It might not even be an ordinal. But it's some chain of submodules. It's well defined when you can take a quotient of one by the next one. And in each case, that subquotient is simple. Then each subquotient is iso to one, to a module like this. and each simple appears at most once. So what I'm saying is you have something that would pass for a Jordan-Helder filtration. You look at the simples that you get there. Okay, they come from the list given in item 1. They might not be all of them, but the ones that appear exactly once. The list might be incomplete, but each one appears with multiplicity at most 1. So I have to say, in point 3, there exists what you would call a Jordan-Helder chain, not a filtration, a Jordan-Helder chain. Right? So a chain, as in the previous item, where every simple appears. So this is a bit of a roundabout way of saying that the module is multiplicity free, right? We're trying to find a way of saying that we have a multiplicity free module, even though multiplicities might not be entirely well defined. There are several ways of doing this. There's a very interesting paper from 2022 by Daisy Rock and someone else who actually try to really get to grips with the situation. This is the way we found to deal with it in our special situation, but it's definitely a work in progress to find the right way to state this multiplicity freeness. And the result probably looks kind of strange, so I want to spend the rest of the time doing a few examples. Okay, I want to show you some examples of how this works. And I will mostly work tensoring with the natural representations because already there, some of the strangest things that can happen already occur. Okay, so let's take a very easy example. We've already done this, right? Okay, so remember that for f to be a highest weight representation, I need to put an order on I such that which has a first element, which has a minimum. And for L to be a highest weight representation, we need a minimum. Sorry, we need a maximum, right? So in order to get, so the theorem at some point promises a total order on I, which will produce a Borel, which will allow me to see the subquotients as highest weight vectors. So let me tell you what that order is. The order I will put on this is the following. I start with a copy of the positive integers, and I end with a copy of the negative integers. Right? So this is like an extension of this idea of indexing everything like computer, like programming languages. There's a bunch of entries, the first, the second, the third, and so on up to infinity. And then there's a second bunch of entries, the last one, the second to last one, the third to last one, and so on. And this set, of course, has a minimum and a maximum. So both F and L will be highest weight. But what's really important first is that L is of highest weight, because in this case, L, I will write it in a, I think you can understand what I mean when I write this as the highest weight, right? This is the indexing set, the one I wrote above. And the entries of the highest weight are 0, 0, 0, 0 in the first bunch of indices. And in the second bunch of indices, you get a 0 almost up until the end. And the very last entry is a minus. So it's minus epsilon minus 1. And the Pieri set, for in this case, is just epsilon 1 and epsilon minus 1. Because the only way you can add something that's in the support of the natural representation to this weight, to the highest weight of L, and obtain a dominant weight is either putting a 1 at the beginning, and then you get a sequence that's 1, 0, 0, 0, 0, 0, 0, 0, minus 1, which is a decreasing sequence and hence a dominant weight. Or you add 1 at the end, and then you get an infinite sequence of zeros, which is, of course, also a decreasing sequence and again dominant. And the previous theorem is going to tell you that if you want to decompose this tensor product, it's going to have a filtration, and the filtration is going to have this Pieri set comes with an order. And our filtration will have at the bottom, yeah, this representation with this highest weight. And then at the top, the representation with this highest weight. And this is what we had seen in the first example, because this representation at the bottom is SL infinity. And the one at the top is the trivial representation. Okay, so this is an example where you recover the previous decomposition of this tensor product. Okay, let's do a second example. Here I want my L to be the highest weight module with respect to this weight. So I'm going to take a minute to explain what I mean by this. So what I'm doing here is I'm indexing my entries by the negative integers. And the weight I'm using, the highest weight, lambda, looks like this. So yeah, so this looks like this. It goes off to infinity to the left. So it starts 1, and then 2, and then 3, and then 4, and so on. With this order, when the entries are ordered by negative integers, this is an analog of the half sum of the roots of GL, right? Well, not the half sum, the sum. But you almost feel tempted of calling this row. But I won't do that. Okay, and I want to understand what is the tensor product between these two things. Okay, I'll tell you what the Pieri set is. What can you add to this sequence, which is a decreasing sequence? Where can you add 1 to an entry such that it remains a decreasing sequence? You can do it everywhere, right? If you add it at the end, then you get 4, 3, 2, 2, which is still decreasing. If you add it in the second position, it's 4, 3, 3, 1. It's still decreasing, and so on. So this is the full support of the natural representation. And this tensor product has a filtration which at the top has a module whose highest weight is lambda plus epsilon 1. Then a second one, whose highest weight is lambda minus epsilon plus epsilon minus 2. And then another one that looks like this. And this filtration goes like that, all the way down to infinity. Okay, it's a separated filtration. Intersection will be 0. This module behaves rather strangely. So this is like a maximally simple filtration, right? This is Jordan Helder style. Each layer is simple and whatnot. But say you want to ask what the radical of this module is. So what's the largest semisimple subquotient that you can get? Well, there is none. The radical of this module is 0. Because each of these modules can be obtained not as a subquotient, but as a quotient of the tensor product. This tensor product is not semisimple. It is very far from being semisimple. It turns out it is uniform. Uniform means that any non-zero submodules will intersect in a non-zero submodule. Okay, so the structure of this module is quite convoluted and not something you often see in Lie theory, at least not when you're working with modules with bounded weights or something like that. So this module has a very curious property, which is that if K is a non-trivial module, so it's not the whole thing and it's not 0, then the quotient is semisimple. Basically, what happens is that you will eventually catch some layer of this filtration and then everything that is below that. And once you cut out that part, the quotient is just the direct sum of the simples that you have left above. So the structure of this module is peculiar, I would say. So maybe not something you often find. Okay, So let me give you a
Pablo,
third. Yes.
yeah, my comment, this looks like a regular module over polynomials in one variable. Not completely, because there you can also have non-semisimple quotients, but it's very similar somehow, the behavior.
Yes. There is something to it, which I cannot make precise yet. We look at it and we say, okay, what does it look like? And it looks like that sort of thing, right? This is, I think, where this idea of trying to define what it means to have a Jordan-Helder filtration in, for a Jordan-Helder chain inside a module would eventually lead you to try to compare those two things. And okay, I want to give another example. Let me just write what lambda would look like. So this is another descending sequence. This time it's indexed by the natural numbers. And again, the Pieri set is the full support of the natural representation. And the tensor product. You will have filtration. Let me tell you how the filtration is defined. It's always defined in the same way. Um, so you will have a module M1, which is just the highest weight vector of my representation L, tensored with E1. And this will be contained in M2, which is just, so by this I mean the GL infinity module spanned by this. And then there's an M3, which is defined just as before. And in the previous case, the definition is quite analogous. It's always the same result. The quotient of consecutive terms is just the corresponding simple you're looking for. This is the filtration that the theorem promises. This one has all the simples in the representation. But in this case, the representation is semisimple. So the filtration is kind of silly because you don't need a Jordan-Helder filtration. You have a semisimple representation. And so, yeah, the behavior of this tensor product is quite, it varies widely. Okay, it depends a lot on, so this order here, the order that you fix, it has to be adapted to the highest weight, so to the lambda, to the highest weight of the L, but also to the type of representation you're taking as an F. If it's an exterior power or a symmetric power or a Fock module, you have to sort of twist it around, not exactly to make the F a highest weight vector, but to make the weights inside the F compatible with the lambda. And depending on how you make those choices and on the choice you have to make, the result might be semi-simple, might be indecomposable, might be uniform, it might be several things. So in order to finish, I want to show you what we did to organize all of this. Because just saying that you have a certain filtration that behaves in a certain way is it's unsatisfactory as a Pieri rule, because the Pieri rule says that a tensor product, in the finite dimensional case, is semi-simple and then proceeds to describe the simple constituents. So in order to give a Pieri rule for GL infinity, I not only want to give you the simple constituents, but I want to tell you something about the semi-simplicity in the composability, something about the structure of the module. Right, so this is like a second part of the theorem. I need to introduce a relatively technical definition here, so please be patient, but then I will tell you what the final general theorem result is. So I'm done with the examples. I will introduce a certain equivalence relation in the indexing set. Right, so the equivalence relation is easy to understand. So my weight lambda is a sum of lambda i's, epsilon i's, and I will say that two indices are related if lambda takes the same value at those two indices. And you take a set J, which is just a quotient of I. So there's an obvious map from I to J. And J is obviously ordered, right? It is ordered in a way that makes lambda dominant, in a way that makes lambda, so lambda is defined as a function from here to here, just by sending a class J to the corresponding lambda I. And lambda being dominant just means that this map reverses the order. So when you take the adapted order, the order that is promised in the theorem I mentioned above, it's just one that makes this whole thing order reversing. Okay, this is where that order in the theorem comes from. I want this to be such that I want that order to imply this. Okay, but okay, so we have this J set. Now this projection map will get a section S where S of a class will be the minimum of the class. And this will be well defined again because the order promised in the previous theorem guarantees that each class has a minimum. Okay, so this is the second condition you impose on the order. Every class, every J class has to contain a minimum element. And there's a second, there's a further equivalence relation between J classes, which is that they are, there's an infinity relation. If when you look at this, so this is an interval inside I, right? You take the first element in the J class, the first element in the J prime class, and you ask them to be at finite distance. This is hard to understand, so I will do a couple of examples before I go on. This is a further equivalence relation. Okay, so out of I, you take a quotient where you identify indices where lambda coincides in those indices. And then there's a further quotient J infinity. I will give you a couple of examples just to make this clear. So if lambda is our last example, then J is just I, because there are no two entries where lambda takes the same value. But J infinity is a singleton, because if you take any two, so every element in J, so every pair of elements in I are at finite distance from one another. But you can do something weird, right? You could take something like 3, 2, 2, 0 to the infinity minus 1, minus 1. Right? So I'm using that order where this is the first element, this is the second one, this is the third, this is the minus, this is the last, this is the second to last, and then there's a bunch of elements in the middle. So then J is a finite set. It's the class of 1, which is less than the class of 2, which is also the class of 3. It's the same as the class of 4, which is the same as the class of minus 3. And then you have the class of minus 2, which is the class of minus. So this is 1, 2, 3, 4, 5 elements. Okay? Because lambda takes 1, 2, 3. Oh, yeah, I made a mistake somewhere, right? Yeah, this is only one. Lambda takes 4 different values. So J has exactly 4 different elements. And what about J infinity? Well, let's see. The first element in the class of 1 is at finite distance from the first element in the class of 2. So these two collapse into a single element. And the same holds for this, right? Because the first element that is whose value is 0 is at finite distance from this element here. But now the first element from this class is at infinite distance from the first element of this class. So there's a second class formed by this. So in this case, J has 4 elements and J infinity has 2 elements. And once you've introduced this set, you can give a very general theorem on the structure of the set M according to what J and J infinity look like. So to state it, let me show you a little table. So the behavior of the module depends on whether J and J infinity have or do not have a maximum. Okay? And the theorem states that before you know anything about J or J infinity, there's a certain filtration you can build. Okay, there's a filtration called C over the module M, and its behavior will depend on what happens with whether J or J infinity has a minimum or a maximum. So let's look at the very nice case where J infinity has both a minimum and a maximum. In that case, you want J to have a minimum, essentially. That's the only thing you really want. J to have a minimum and J infinity to have a minimum and a maximum. In that case, this filtration, which is built a priori before you know anything about the module, is both a Sokal and radical filtration. So the module has finite length, it has a Sokal filtration, a radical filtration, and it's what you would call rigid. It's got only one filtration with maximal semisimple layers. Simples cannot just move around inside that filtration. So it's a very rigid module. It is indecomposable if and only if J infinity has at least 2 elements, which means that there has to be some value of lambda that is repeated infinitely many times. If not, then the module will be semi-simple. Otherwise, it's indecomposable. So these are the 2 extreme cases. It's either semi-simple when J infinity is just a singleton, and in any other case, it's indecomposable. And how do we know this? Because for this filtration, this radical Sokal filtration, we know all the links inside that filtration. We know all the links between simples inside these tensors. So this is the nice case. There's a slightly less nice case when J infinity doesn't have a maximum. In that case, our coarse filtration coincides with the Sokal filtration. A posteriori, we know that it coincides with the Sokal filtration, but it's infinite. So for example, its Levy length is infinite, its length is infinite, and the module is always indecomposable in this case. Okay, so this is like the nice corner of this table. When both J and J infinity have a minimum, then we have a pretty good control of the module in terms of very classical, stuff that you would often see when trying to describe modules in some Lie theory category. Okay, so what happens when J doesn't have a minimum? That's the worst possible case. If J doesn't have a minimum, but J infinity does have a minimum, then the filtration is very, very complicated. It may or may not coincide with the radical filtration, but it will definitely not have semi-simple layers. This is similar to the first example, the second example I showed, where the module turns out to be uniform. The modules, the submodules are just really tangled up. Any 2 non-zero submodules will intersect in a non-zero submodule. The internal structure of this module is hard to find, hard to understand. And the worst case is this one here. So in this case, J doesn't have a minimum nor a maximum, and J infinity only has a minimum, but not a maximum. In this case, there are no Sokals, no radicals. You cannot study these modules with such tools. This is where most of let's say the basic definitions just don't cut it. And yet, when you move on to this case, where suddenly neither J nor J infinity have a minimum, things sort of work out. Suddenly, this filtration, which is not the Sokal filtration and it's not the radical filtration, because the module has no Sokal, it has no radical, it's hard to understand in these terms. But this filtration that you can define a priori has semi-simple layers. And in fact, to be checked, we think it's the unique maximal filtration with semi-simple layers. So any filtration with semi-simple layers will be what's the word? This is like a coarse filtration. It will be a refinement of this coarse filtration. Somehow it does what the Sokal or the radical filtration sort of do. It's maximal in a sense, even though there is no Sokal or maximal filter or radical filtration for this module. And again, the module is in decomposable. The cases which are struck out are impossible because if J infinity is a quotient of J, so if J has a maximum, J infinity has to have a maximum, and so on. So you essentially have this sort of division is sort of a red herring. What's really important is this. There's a nice corner here where things behave as you would expect. It's almost as good as you can expect for GL infinity. The upper right corner is where everything just blows up. And then for some reason in the bottom right corner, when conditions seem to get worse, for some reason they get better. We're still trying to understand exactly why this situation here improves. And that's all I have for you today. Thank you very much for your attention.